We propose dynopets, a versatile benchmark for dynamic object pose estimation and tracking in moving camera scenarios. We introduce our work in 5 parts. At first, object pose estimation aims to determine the position and orientation of an object. This task has wide applications in augmented reality and robotic arm manipulation, enabling precise interaction with real-world objects. Our motivation stems from the need for simultaneous camera ego motion and object dynamic scenarios, essential in real-world tasks. Currently, lack of accurately annotated real-world datasets, mainly due to high manual costs, scene constraints when using motion capture devices with objects, and inaccuracies in pseudo-labeling methods. Our contributions include an efficient annotation pipeline, a novel dataset, and systematic benchmarking on corresponding tasks. Our pipeline includes CAD model preprocessing and hand-eye calibration on the left. On the right, we capture dynamic objects with a moving RGBD camera, annotating poses by combining absolute and relative poses. Only the camera poses are captured by mocap. After recording the RGBD videos, segmentation is performed using SAM2. We use an iPad Pro equipped with structure sensor to capture dynamic objects under a moving camera. Initially, static recordings align visual odometry with mocap data to synchronize timestamps, ensuring precise video and camera pose alignment. Then, we first apply a model-based tracking method to estimate initial absolute object poses with the forward pass of the EKF, followed by RTS smoother to refine these pose estimates. Then, we employ a point tracking method to directly monitor changes of 2D points on the object. Specifically, this approach is critical for textureless or highly rotationally symmetric objects, particularly when model-based pose tracking struggles to yield accurate results. As illustrated here, the pan's relative pose estimation remains notably stable. We then feed absolute poses and relative poses into a pose graph under local coordinate system, producing accurate poses. We compared poses directly obtained from OPT with our PGO outputs, clearly highlighting improvements from our efficient annotation method. Our dataset comprises COPE 119 covering 6 common object categories, and UOP 56 subsets for category level and instance level or unseen object pose estimation tasks. We've also provided clear train test splits, offering substantial contributions to both COPE and IOP research. Here we present the quantitative results for the COPE methods. As shown, performance severely degrades when objects are grasped, causing significant changes to top-down or tilted viewpoints. After fine-tuning AG pose and second pose on the COPE 119 training set for just 2 epochs, we observe obvious performance improvements on the test set, especially notable when objects are grasped, demonstrating our dataset's substantial impact on the object pose estimation field. Here we also present the quantitative results for the UOP methods. Finally, we present object pose tracking results. It demonstrates that some existing approaches exhibit noticeable drift under certain conditions over time. Thanks for watching.